Welcome all. My name is Dr. Hanu Phani. I am Assistant Professor in the Department of Biomedical Engineering. Today we are going to discuss digital logic circuits, in that a topic named number systems and its conversions. So let us start the topic. In this physical world, we generally represent any particular physical entity either by its name or its quantity in terms of numbers. So to represent any quantifiable object, we generally represent it with numbers. From childhood, we are seeing decimal number system. We learn decimal number system. That is what we understand. But if you see the systems, machines, they cannot understand this decimal number system. They tend to understand different number system. So today we are going to discuss about the 4 basic number systems that are existing, especially pertaining to digital logic circuits. So the first number system is a decimal number system. So in this number systems, the 3 things we need to remember. One is the name of the number system. Second one is the base or the radix of the number system. And finally, what are the different digits that are there in this number system. So the first number system is a decimal number system, where we can see the base of this number system is 10. What do you mean by this base or radix? Generally, the base or radix is nothing but it's the number of digits that are there in the particular number system. So number of digits in the number system. In the case of decimal number system, the number of digits are from 0 to 9. That means there are 10 digits in the decimal number system. As I said, the machines cannot understand this decimal number system. Therefore, we are learning this number system known as binary number system, wherein the machines can understand only zeros and ones. As I said, the base is the total number of digits. In the binary number system, the total number of digits are 2. Similarly, along with these 2 number systems, there are 2 more prominent number systems. Those are octal number system and hexadecimal number system. As the name signifies, octal means 8. So therefore, there are 8 digits in this octal number system. The digits are from 0 to 7. Finally, we'll also learn about the hexadecimal number system. Hexadecimal number system contains 16 digits. So as I said, 0 to 9 is similar to decimal number system, whereas decimal 10 is A, 11 is B, 12 is C, 13 is D, 14 is Z, 15 is F. This is how the hexadecimal number system exists from 0 to F, where 0 to 9 similar to decimal numbers, whereas 10 to 15 is represented as A, B, C, D, E, F in the hexadecimal number system. To understand more about this number system, let us understand with an example how these numbers are represented. For example, as I said, each number system has a base. The decimal number is represented from 0 to 9. So for example, let us take 123. So how do we know whether this is decimal number or not? So we have to represent each number with a base. So the decimal number system has a base 10, therefore it is represented as 123 base 10. But any number has 2 parts to it. One is the integer part, other is a fractional part. For example, the same number can also have a fractional part. Let us take a small example, 256.23 base 10. So this is integer part, this is a fractional part. Similarly, binary number system is the combinations of zeros and ones. How this is represented? Let us take small example, 0 1 0 1. This can be represented as base 2 since it is a binary number. This can also have both integer as well as fractional part, 0 0 1 0.001 base 2. So it also contains both integer part as well as the fractional part. Now we can also see the same way octal number. As I said, it exists from 0 to 7 with a base 8. So we can write octal number as 17 base 8 with a fractional part also 17.016. This is also octal number. If someone write a number like this, let us think someone write a number 165. How do you know which number is this? It can be both decimal number as well as octal number. So this, until and unless it is defined with a base, you cannot say whether it is a decimal number or octal number. So until and unless it is mentioned as base 8, it can be decimal or octal. Therefore, this writing of base is very important as common digits are there in multiple number system. Okay, so this is octal, this is decimal. Finally, when we come to the hexadecimal system, similarly, a number can be, let us think 1A, B. So this is a hexadecimal number. As I said, A signifies 10, B 11 up to F, which is 15. So we can also have F integer part as well as the fractional part. Okay, so this is how this is integer, this is fractional. Similarly, this is integer, this is fractional. So this is how different number systems, this is how we can see there are how we represent different number systems. Next, so these number systems, it is very important to understand what are weighted codes, because the decimal number system has a unique quality. Not only decimal number system, other number systems has a unique quality wherein each and every digit has some weight to it, from which we can understand these are weighted codes. For example, this 235 is nothing but this can be written as 5 into 10 power 0, 3 into 10 power 1 and 2 into 10 power 2. So why I am writing like this? It's because at each and every place it has its weight. For example, the least significant bit has the weight of 10 power 0, and afterwards if you go from right to left, these weights increases. For example, at this second bit we have weight of 10 power 1, third bit we have weight of 10 power 2. And how we get this number? We get this number by multiplying the digit with that weights and adding it. This is how any decimal number is represented. In the same way, we can convert any number, okay, to a decimal number by using these weights that we will learn in the next slide. So along with this weighted codes, there are also non-weighted code. That means there are no weights to each and every code of it. For example, so when we come to the non-weighted code, each and every code of it is represented with a specific number, unlike the weights. For example, here this is nothing but x1 v is nothing but it's 14, where the x represents 10 plus 1v represents 4. Okay, that's how we'll get 14. It's not a weighted, it's just a representation. Similarly, we have something known as gray code in the digital logic circuits, wherein these gray codes vary from one code to other code by only one bit. How these are formed, we will learn in the later section of the classes. So this is just to understand the number systems are weighted like this decimal number system. It's a weighted wherein each digit has a weight to it. Now we'll try to understand the conversion of one number system to other number system. In the first number system which we are converting is from the decimal number system to the other number system. So decimal number system, we already told it's a base 10. So I want to convert a number, let us take any number like for example 100 of base 10. I want to convert it into base 2, or I want to convert it into base 8, or I want it to be converted into base 16. So there is a procedure for this. So what is the procedure? Any given number. So here it has only integer part. Let us take some other number like 100.10 base 10. So now I want to convert it into the other number system. How do I do it? There is a process to it. First, what we have to do? We have to separate the integer part as well as the decimal part. What is the integer part? Integer part is 100. The decimal part is 0.10. So what we have to do with the integer part? Integer part should be divided with the base r. Base r or radix r is nothing but the radix of that number system which we are going to convert from the decimal number system. Let us take, we are converting from decimal to binary. So we have to divide it by 2. So when we divide it by 2, so here 100 is divided by 2 by 50, quotient is 50 and the remainder is 0. Similarly, we have to divide up to an extent wherein the number becomes 0. So I'll also try to explain with an example. For example, this 25, again it is 0. 12, remainder is 1, 2, remainder is 0, 2, remainder is 0. So we have to continue these steps up to wherein the number becomes 0, and we have to take these reminders from bottom to above in the reverse order. So this is how we have to collect all these binary digits. This is how you will convert from the integer part to other number system. For example, now you want to convert it into octal number system. What you have to do? You have to do the same procedure wherein you have to divide it by 8. Similarly, if you want to convert into hexadecimal, you have to divide it by 16. So that, and once you get the reminders, you have to take it from in the reverse order. So that will be the integer part. In the case of fractional part, what you have to do? We have to multiply, for example, 0.10, we have to multiply by that radix. For example, if I am converting into the binary number, I have to multiply by 2. What I will get? 0.2. I have to consider the integer part of this result. That means integer part is 0. Next, I have to take this fractional part, 0.2. Again, I have to multiply by 2. 0.4. The integer part, again, it is 0. Fractional part is 0.4. So I have to continue this process until up to certain decimal points, up to 4 or 5. then I have to collect all the digits in the same order as I calculated. Then therefore I can calculate the fractional part. If I want to get the fractional part in the octal number system, what I have to do? I have to multiply it with the 8 and follow the same procedure. In the case of hexadecimal, I have to multiply 0.1 with 16 to get the same in the same procedure. This is how we calculate decimal to octa other number system, like a decimal number, decimal to binary, decimal to octal, decimal to hexadecimal number system. So let us see more examples clearly how we do this in the decimal to binary number system. Everything is same here, except now we are clearly dividing it by 2 in the case of integer part, and multiplying it by 2 in the case of the fractional part. If you see this example, we have a number. This is the case in which you are converting 239.634 base 10, which is of decimal, to the binary number. As I said, first you have to take the integer part, you have to divide it by 2. So when you divide it by 2, you will get a quotient 119 and you will get a remainder. Similarly, again when you divide, you will get a quotient, you will get a remainder, until and unless the quotient is 0. So when you get the quotient 0, you have to collect all the reminders from the bottom, like 1 1 0 0 1 1 1 1. So that is the result of the integer part in the binary. In the case of fractional part, you have to multiply by 2. When you multiply by 2, you have to collect the integer part. For example, 1.268, the integer part is 1, and fractional part, again you have to multiply by 2. Here integer part is 0, here integer part is 1, 0, 0. So therefore, the fractional part here is 10100, and integer part as I explained. This is how we convert a decimal number to the binary number. Let us do a small example. 150.33. First step is to separate the integer part and the fractional part. The integer part is 150. So what I have to do? I have to divide it by 2. Quotient is 75. Here the remainder is 0. Again, when you divide it by 2, it is divided by 37. Remainder is 1. Again, it is divided by 18. 2 times 36, the remainder is 1. 2 9 times, remainder is 0. 2 4 times, remainder is 1. 2 2 times, remainder is 0. 2 1 times, remainder is 0. 2 0 times, remainder is 1. So the answer is decimal part 150 base 10 is nothing but we have to collect the reminders from the bottom. It is 1 0 0 1 0 1 1 0 base 2. And the next step is we have to take the fractional part. Fractional part is 0.33. What I have to do? I have to multiply by 2. When multiply by 2, it is 0.66. The integer part is 0. Take the fractional part. Again multiply it by 2. It is nothing but this is 1.16 plus 32. Here integer part is 1. Again 0.32 multiplied by 2. It is 0.64. Integer part is 0. Again 0.64 multiplied by 2. It is 1.281, and this goes on. So here 0.33 base 10 is nothing but we have to collect all the reminders from the same order or from the top. It is 0 1 0 1 so on, 0.0101. So the complete answer is 100 10.0101 base 2. So this is how we convert from the decimal to the other number system, that is binary number system. And the other way around, what is the other way around? We have to convert it from the other number system to decimal number system. So there is a procedure for this. Let us understand how to convert any number system to a decimal number system. Let us take an example. Let us take a number dn, dn minus 1, dn minus 2 up to d0, point d minus 1, d minus 2, d minus 3 and so on. Let us think that this is of radix r. So how to convert it into a decimal number system? This is any number system. So these are the digits and this is the base r. How to convert it into a decimal number system? There is only one way to convert it to a decimal number system. We have to use the weights of that base and multiply with each of the digit. So how we convert? So this dn is multiplied with base power n plus dn minus 1 is multiplied with r power n minus 1, so on. d0 is multiplied with r power 0 plus, in the case of fractional part, it is d minus 1 multiplied by r minus 1, d minus 2 multiplied by r minus 2 and so on. So if we do this, this will get converted into base 10. This is how we convert any number system of base r to a decimal number system. So let us try with a binary number system. So how do we convert? Now take the binary number 101.11 base 2. As I said, each of the digit has its weight. Here base is 2. So the weights are 2 power 0, 2 power 1, 2 power 2. Here 2 power minus 1, 2 power minus 2. By looking at this, how to do this? It's nothing but 1 into 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0 plus 1 into 2 power minus 1 is nothing but 1 by 2 plus 1 into 2 power minus 2 is 1 by 4. This is nothing but, this is 4 plus 1 5, this is 0 plus this is 0.5, this is 0.25. So this is nothing but 5.75 base 10. This is how we convert the binary number system into the decimal number system. Similarly, we can do this example. So how do we convert octal to decimal? The same way, 75.3. Okay, so write the weights on the top. This is 8 power 0, 8 power 1, 8 power minus 1. So this is nothing but 7 into 8 plus 5 into 8 power 0 plus 3 divided by 8. This is nothing but 56 plus 5 plus 0.3 0.375. So the answer is 61.375 base. This is base 10. So this is how you convert octal to decimal. Similarly, we can do the same thing for hexadecimal to decimal number system, where this is hexadecimal 7A2.C9. So this is 16 power 0. These weights are 16 power 0, 16 power 1, 16 power 2. This is 16 power minus 1, 16 power minus 2. So this is nothing but 7 into 256. As I already discussed, A represents 10 in the hexadecimal. A in the hexadecimal number system represents the 10 in the decimal number system. To 16 plus 2 into 16 power 0, that is 2, plus C. C represents A is 10, B is 11, C is 12. It's nothing but 12 by 16 less 9 by 256. It's nothing but 1792 plus 160 plus 2, 4 3s are 4 4s are 0.75, and this is some point 0.035. So this is how we can further add all these things. We'll get 162, 1792, so this is nothing but 1954.785 base 10. This is how we convert the hexadecimal number to the decimal number system. So there are two important systems apart from the decimal number system and binary number system. Those are octal number system as well as hexadecimal number system. As I said, octal number system as a base 8. So why we are studying this octal and hexadecimal number system is, it's a compact way to represent the binary number system. So how we represent the octal to the binary is 8 can be represented as 2 power 3. So this 3 signifies that any octal number can be represented using 3 bit of binary numbers. For example, you can see here the 0 can be represented as 000, 1 can be represented as 001 up to 7, which is the binary equivalent is 111. That means 7 is equal to 111 base 2. 7 of octal is equal to 111 of base 2. So this is how any octal number can be represented with a base with a 3-bit binary number. So how to convert? So this is important that we convert from binary to octal. It has many applications. For example, in the computer architecture, octal number and hexadecimal number system is mostly used because it's a compact way of representation of the binary number system. So how to convert this binary to octal is, there are The same way we have to separate the integer part and the fractional part. So let me explain it through the examples. In the examples, we can see here, this is the integer part. How to convert it into octal number system is, we have to, let us see through the example how we'll convert the binary number to the octal number system. So first what we have to do is, through the integer part, we have to scan the numbers from the least significant bit. This is least significant bit. So we have to categorize into 3 bits from the least significant bit to the higher significant bit. So we have to move from right to left. With the 3 bits, we have to group them and convert it into the corresponding octal number. For example, the first 3 bits corresponds to 0, 0, 1, 1. So 0, 1, 1 corresponds to, in the octal is 3. Next 3 bits are 0, 0, 0 is nothing but 0. The next 3 bits are 1, 0, 1. 1, 0, 1 is nothing but 5 in the octal. Then again 1, 0, 1 is 5. So this is nothing but 5503 base 8. Similarly, again in the second example, let us see. We have to group from the least significant 3 bits. 1, 0, 0, 1 corresponds to 1. Again 1, 0, 0 corresponds to 4. 0, 1, 0 corresponds to 2. So here there is an interesting aspect. You can see there is only 1 bit. What you have to do? So you have to add zeros in such a way that we'll get a 3 binary bits. So in the leading end, you can add 2 zeros to it. That means you can add 0, 0 here. That means here you get 0, 0, 1. It's nothing but 1, 2, 4, 1 base 8. This is in the case of integer part. In the case of fractional part, you have to go from the left to right, and you have to group in the, you have to group 3 bits. For example, here point, the first 3 bits is nothing but 4. Next 3 bits nothing but 1. As I said, here similarly, since we have had zeros, here also we can add zeros, because it doesn't matter after the decimal part. It doesn't matter how many zeros we add. To make it 3 bits, we can add 0, 0, 1, 0, 0. So this is 1, 0, 0 is 4. This is of base 8. So this is how, through example, we can understand. In the case of integer part, we have to go from the least significant bit to the highest significant bit. We have to group in 3 bits to convert it into octal number. If we have less number of bits, we can add zeros. In the same way, in the case of fractional part also, we can have to group from right, left to right. And in the case of missing bits, you can add zeros, as it doesn't matter. So this is how we got the result. As I said, here we added 2 zeros, and here also we added 2 trailing zeros to get the result. In the same way, we can also, in a similar way, we can convert octal to the binary number system. How to do this? Each bit of the octal can be represented as a 3-bit binary data. For example, 1645 is nothing but 1 is represented as 0, 0, 1, 6 is represented as 1, 1, 0, 4, 0, 1, 0, 0, 5 is represented as 1, 0, 1. This is how you can convert the octal to binary data. Similarly, 2 is represented as 0, 1, 0, 0, 1, 0 dot 0, 0, 1, 7 is 1, 7 is 1, 1, 1, 2 is 0, 1, 0, base 2. This is how it is represented. And as already said, we can convert any number to the octal, that means decimal to octal, by dividing it by 8 in the case of integer part, multiplying with 8 in the case of fractional part. We already discussed this. So similar to octal number system, hexadecimal number system can be represented in the binary, but as I said, hexa is 16, which is represented as 2 power 4. So each hexadecimal number bit can be represented in 4-bit binary data. So A is represented, we already seen that 0 to 9 is similar to decimal number system, but from 10 to 15 is represented from A to F. So in the same way, we can convert from binary to hexadecimal number system. Let us see through the example. So in the case of octal, we have selected 3 bits. In the case of integer part, we have to go from least significant bit to the higher significant bit. We have selected in the octal 3 bits. Now we have to select 4 bits. Select these 4 bits from the least significant bit. This is nothing but 3. This next 4 bits is nothing but, this is 4. This next 4 bits is nothing but 1011 is nothing but 1011 is nothing but, sorry, 1010 is 10, 1010, 1011 is 11. This is A, this is B. So therefore, this is nothing but 1011 is B, base 16. Similarly, 4, this is 1, this is A, and this is, you can add 2 zeros to it, because to get 4 bits, this is 1, this is nothing but 1A1 base 16. Similarly, in the case of fractional part, we have to go from the left to right. First 4 bits, this is nothing but 1000 is nothing but 8, and this is nothing but, we have to add one more 0, this is 4. This is 0.84 base 60. You can see here, this is how we calculated. So there is a mistake here. This 0010 is nothing but 2. It's not 1, it's 2. So similarly, we can convert hexadecimal to the binary. So wherein each bit or each digit of the hexadecimal can be converted into the 4-bit binary. For example, A is 1010, B is 1011, C is 1100, D is 1101. Okay. So 3 is nothing but 0, 0, 1, 1. A is nothing but 1011, 1010. 5 is nothing but 0, 1, 0, 1. Okay, this is base 16. Similarly, 1 is nothing but 0, 0, 0, 1. 2 is nothing but 0, 0, 1, 0. 0.3 is nothing but 0, 0, 1, 1. D is nothing but, it is 1, 1, 0, 1 base 16. This is how we'll convert the hexadecimal to the binary number system. So in summary, we have discussed about the different number systems, mainly the 4 number systems, and we have also seen the different conversion mechanisms by which we can convert one number system to other number system. What is the need of this conversion? As I already said, so for example, binary digits can be understood by machines. Therefore, we need to convert from one number like decimal to binary. And why we are converting it into octal and hexadecimal? Because they have their own advantages, wherein octal and hexadecimal numbers are the representation of the compressed form of the binary number system, wherein octal we use 3-bit data of binary to represent octal. In the case of hexa, we use 4-bit binary to represent the hexadecimal number system. So this is how we have learned different number systems as well as its conversions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.